we're going to talk about exam 2 first, and then we're going to continue. Okay? So, when do you going to have exam?
Oh, Wednesday. No. The 16th.
Oh, you said when do we want to?
Yeah, I vote Wednesday.
Oh, Friday the 18th.
No, I have another exam that day.
So, Friday going to be a little bit late. Remember, you're going to have the exam 3rd and 4th, right? So, if you push later, you're going to have about 2 weeks for the exam 4. So, you don't have that. So 14 gonna be just right in terms of schedule, but if you have changed it, I'm open to it.
January 14th, Wednesday.
2025?
Okay. How about Wednesday the 16th? I just said that. We're revisiting it. How about the 16th?
No, that means
So-
the 11th would be.
So here's the thing, like chapter 7 is very short. We're going to finish in 1 day, probably 1.5, something like that. So you're going to have very few questions from chapter 7. Okay? So you're going to have mostly chapter 5 and 6. So we're going to have enough time to review it. We're going to do on 14.
Okay.
Alright? So probably we're going to finish 7 on Monday. And then we're gonna have Wednesday and Friday. If you can have a little bit longer review, I can do that.
Yes, please. That would work.
Can we
Okay.
please have some practice questions like last season?
Yes, I can do that.
Thank you.
So then 14 gonna be okay, right?
Yeah.
All right.
Good.
So exam
me.
gonna be on 14.
Okay.
Okay. So I'm gonna provide questions by maybe today or tomorrow. Okay. So you're gonna have more than 1 week to go over it, and then you're gonna have more than 1 day at least 1.5 class for the review. Okay. Yep.
What chapters is it going to cover?
Chapter 5, 6, 7. Okay. Good. All right.
Getting to review is like.
All right, let's review a little bit of the last class, right? So we were talking about the stereoisomers, how to name that with R and S, right? And also based on the experiment you do, how you're gonna rotate the light. You're gonna have a D or L. You're gonna have plus or minus. Okay? So now here is the example. So it says, what going to be your notation for this molecule based on the experimental observation. So it is given. So you have molecule that going to rotate light in the clockwise direction. That is given. There is the molecule. If you pass the light to it, it's going to rotate to clockwise direction. Right? Then for that, what's going to be the rotation? D or L? Plus or minus? Both are same thing, okay? So D is same as plus, L is same as minus. So either you're going to note by D or plus, or you're going to note by L or minus. What do you think?
D.
D plus, right?
Yeah.
So if you have clockwise, it's going to be D plus. If you have counterclockwise, then going to be L or minus. Okay? So now you know the answer. But now I'm going to ask one question. Okay? Why this is R over here? So, do you think it is typo or the right notation for this model? Okay, let me simplify a little bit. Okay? So, this is your chiral carbon, right? You have 4 groups that are different attached to that carbon. So you have the hydrogen, it is not shown there. So I'm gonna write hydrogen like this, right? So this is hydrogen. So this is 3D structure. So now I'm gonna number the atoms based on the atomic number. Okay? So for the first, you're gonna have all tie. Okay? So I'm gonna indicate that. So you have this carbon bonded to that, this carbon bonded to that, and then this one. So you have 3 carbons that are tied. They have the same atomic number for 3. Yep.
So that it should have redemptions.
Um,
It should be bonded.
That was the question. Okay, that's the one I'm trying to explain. Okay, so you got it. So now, what gonna be? What gonna be the carbon? This one. So which gonna be number 1 carbon? Tell me. So this gonna be number 1, right? Why? You have 3 carbons bonded to that. And then which gonna be number 1? Number 2. I can write this one because you have 2 carbons bonded to that. You have double bond there, right? And then this is going to be number 1. You have only 1 carbon there. Okay, so whenever you have the double bonded or triple bonded atom, you're going to count like 2 or 3 times of that. Right? So that's how you're going to do the priority. So now, if you see over here 1, 2, 3. So this is 3. 1, 2, 3. So going to be counterclockwise, right? Supposed to be yes.
So it's out.
Uh-huh.
So it's the left side?
Yeah, it is counterclockwise. You go 1, 2, 3.
So it's at.
Yes, right?
Uh-huh.
So I'm gonna write yes. It is typo then?
Well,
No.
wait, no.
It's right. Remember? So what is the orientation of number 4 over here? See that? So number 4 is pointing towards the rear. That's not how you're gonna name the compound. Number 4 should be on the back all the time. Okay, so you're gonna flip the molecule first. So hydrogen number 4 gonna be on the back. Okay, so if I flip that, so what it's gonna look like? So I'm gonna flip that. So this is molecule. So methyl gonna go over here, and then double bond gonna be over here. I'm gonna just flip by 180. Okay, so after that, the carbon you have, this carbon, which is chiral, right? So when you flip, the hydrogen is going to be on the dotted line, and the other group going to be bold face. So I'm going to do this first. I'm going to do the bold line for this carbon, like that, and then I'm going to make the hydrogen on the back. That's the first thing I'm going to do. Then I'm gonna number. Okay, so this is gonna be number 4, of course, and then you're gonna have this number 1 carbon over here, and then number 2 gonna be this one, number 3 gonna be this one, right? So now, what is the rotation? Clockwise gonna be R. Okay, so don't be confused with that. So whenever you name it, make sure the number 4 atom is on the back, always. And then you're going to number and then see whether you're going to have clockwise or counterclockwise. So that's how you're going to do. Still confused? I'm gonna show you this one. So here, what you are having is like this, right? Suppose carbon number 1 is this one. Okay? So you have the ring. So if you see from your side, right now it is like this. So your carbon is on the back, right? You have the hydrogen on the front. So if I flip the molecule like that, then now you're going to have the number 1 carbon on the front, hydrogen on the back. You're going to flip like that, and then you're going to see the number. Okay? So that's how it goes. Alright. So now, the next thing is how you're going to express the rotation of light. It's like concentration of solution. If you recall your Jetchem, you have different terms for the concentrations of solution, right? One gonna be molarity, other gonna be percentage, or mole fraction, or molality. You have so many different terms for the concentration. The concentration is the same thing, right? So how much solute you have in the solution. That's the whole idea. So you have a different way of expressing that. Out of these many, molarity is the very common one. So when you do the experiment in the lab, you're going to say 1 molar, 2 molar, 3 molar concentration, something like that. So we always focus on the molar concentration because it is easier to handle it. The same thing. So whenever you see how much light is going to be rotated for that molecule, the specific rotation is the term we're going to use for that rotation. Okay? So you have the formula for that. The specific rotation is the observed angle you're going to see. So 10 degree, 20 degree, 30 degree, whatever you observe in the experiment, you're going to take that value and then you're going to divide that, you're going to scale that number by the length of the glassware you're going to put the solution in. That's the length of cuvette, for example, right? So you have the Beer's law experiment. Remember, you had the small cuvette. It was 1 centimeter in width, something like that. Right? So you have the certain tube or cuvette to have the solution. You're going to take the width of that, length in diameter, length of the solution, or you can say width of the glassware. Okay? And the concentration, gram per 100 ml. It's like a percentage. So how many percentage you have solute there. So if you divide by that, that's the specific rotation. So that's how we're going to express. So this is the notation for that. Alpha in the square bracket. So that's the notation for this specific rotation. Okay. So that's how you're going to report that. So now, if you take the enantiomer D and L, plus and minus, for the same molecule, you're going to have D and you're going to have a L, right? So for that, you're going to have the equal amount of rotation, but of course going to be different sign. Right? So for example, you can see 2-bromobutane. So there's the molecule. So you can have the S or you can have the R isomer of that, right? The stereoisomer. So one is going to rotate this to the clockwise, and the other going to rotate the same amount to the counterclockwise. You're going to have the same magnitude of rotation, but one is going to be in one way, other going to be in the other way. Okay, so that's how you're going to have. So this is for the enantiomer pair. So you have one pair, You have two molecules over there. One molecule gonna rotate in one direction, other gonna rotate in the other direction. Okay, you're gonna have the equal magnitude. Okay. So now we're gonna go to a little bit. It's not that confusing, but a little bit confusing than just a simple enhancement. Okay. So up to this point, we see the examples that you have one stereocenter or one chiral carbon. Okay? So these are the cases we saw in many different examples. Okay? So now, what if you have more than one? Say you have two chiral carbon or three or four, right? So what's going to happen if you have many chiral carbons in the molecule? So in principle, how many gonna be? Gonna be like this. So if n is the number of chiral carbon in the molecule, the total number of stereoisomers gonna be 2 to the power n. There's the formula for that. Okay? So you're gonna have 2 to the power n number of stereoisomer. Right? Where n is number of chiral carbon in the molecule. So if you have only one chiral carbon, 2 to the power 1 is 2. You're going to have 2 stereoisomers. So you're going to have one pair of enantiomers, right? There are the 2 isomers there. If you have 2 stereocenters, then you're going to have 2 to the power 2, which is 4. You're going to have 4 total number of stereoisomers. If you have 3 chiral center, then 2 to the power 3 is 8. You're going to have 8 number of stereoisomers. Okay? It doesn't mean that all 8 stereoisomers are enantioisomers. Okay? They are not. You have some enantiomer and then some other that is called diastereomer. Okay? So now let's go to the diastereomer. So that's the one we were focusing over here. So diastereomer. So now how to define that? So this is the stereoisomer that are not mirror images. So this is different than the enantioisomer. Right? So remember, for the enantioisomer, you have the mirror image of the molecule, right? Of course, if it is chiral carbon, that's going to be non-superimposable. Right? So image is different than the object you have. If it has the chiral carbon, so this is enantiomer, right? But for the diastereomer, still you're going to have the chiral carbon there. But you're going to have more than one stereoisomer, so one going to be enantiomer and the other isomers going to be not enantiomer. So these are diastereomer. So these are not mirror images. Okay? So let's see the example. It's going to be clear. So here, how many chiral carbons you have for this molecule? 1, 2 dimethyl cyclohexane. Right? It is 6 because both metals are on the one side of the plane of the ring you have. So it is cis molecule, right? So now this is not chiral carbon. You have 2 hydrogens there. You have 2 hydrogens. So these 4 crossed carbons are not chiral. Right? Remember, to be chiral, you're going to have the 4 different groups attached to that. Right? So in all those crossed carbons, you have 2 hydrogens. So it doesn't satisfy to be chiral carbon. Okay? What about the one with the bond with dotted hydrogen. So this is chiral, right? So I'm gonna write star for that. So sometimes chiral carbons are indicated by star notation on that. Okay. So this is one chiral carbon. And then I'm gonna have the other chiral carbon. So this one. So two chiral carbons over there. Right? So how many stereoisomers gonna be there? 2 to the power 2, 4. You're gonna have the 4 total stereoisomers for that. Right? So now, if you take this, and then you're gonna put the mirror, so this is the mirror over here. So what image you're gonna see? The one in the mirror is the image of that. Okay? So you're gonna have the hydrogen on the back, of course, here. It's not shown. So you're gonna have the hydrogen there. And then you're gonna have the metal. So if this is the plane of the ring, so the metal is gonna be towards the mirror. If you put the mirror over there, metal is gonna be closer in the mirror. So that's why you're gonna see metal there. Hydrogen is gonna be on the back, right? So back hydrogen is gonna be on the back in the mirror. Okay. So now these two are enantiomer, right? So enantiomer. So you're gonna have the pair of that. So you have the mirror image that is not superimposable. So that's the enantiomer. Okay. So now I don't take the image of this molecule. But what I'm going to do is I'm going to change the position of one metal from one side of the plane to the other one. Okay? So I'm going to send back the red box metal over here. So this metal, I'm going to make that to the other side. So now, you have the trans, right? When you do that, you're going to have the trans molecule. So other than that, there is nothing changed in the molecule. You have the same number of atoms, you have the same type of bonding, everything is same. The only difference is you have the different position of methyl groups in the trans compared to cis. Okay? So now this trans is not enantiomer of the cis. Why? Trans is not the image of cis you have. You have to have image to be enantiomer. It is not image. It's not enantiomer. Right? It is called diastereomer. Okay? It is not a mirror image, so it should not be the mirror image of the molecule. But everything else is similar, just it has the different position of the group in one side or other. So that's going to be the diastereomer. Okay? So this is also stereoisomer. Remember, stereoisomer is not only enantiomer. So the both enantiomer and diastereomers are stereoisomers. Okay? So for the diastereomer, you don't have the image of the molecule, but for the enantiomer, you have the image of the molecule. That's the difference. Okay? So let's see more examples. This can also clarify more. Let's see this molecule over here. It is 3-hydroxy 2-methyl butanoic acid. Okay? So we haven't gone through the carboxylic acid. We're gonna name these compounds later when I go to the functional group. But it has OH there, COOH, right? And then you have the methyl group, right? So you have branches there. One is OH there, right? Other going to be CH3. And then you have the functional group, carboxylic, right? So now how many chiral centers there? You can count the star, red star written there. So you have two carbon atoms with different group attached to that, right? So you have two chiral carbon centers. So now you can change the position a little bit. So let's say A, in which you have the OH and methyl group going to be in the same side, right? And then the other one, B, so you're going to just flip that. So both methyl and OH going to be on the back side. You're going to make on the back side. And then C, one in one side, so methyl on the back, and then OH is going to be on the front side. And then D, you have, so just a reverse of C. So you have the OH on the back now, and the methyl going to be on the front. Okay? If you see A, B, C, D for all, the only difference is the position of group you have in the space. Everything else is same. They have the same bond, same number of atoms, everything is similar, right? So only the position. So these are all stereoisomers. So you have two chiral center, 2 to the power 2 gonna be 4. So A, B, C, D, you have 4. So these are all stereoisomers. Okay? So now the question is, out of these 4 stereoisomers, which are enantiomers, which are diastereomers? So you're gonna separate based on the mirror image. So whatever you have the image of the molecule, that's gonna be the enantiomer. Whatever you have not image of the molecule, then that's gonna be diastereomer. That's simple. Okay? So, of course, the easy way is cis and trans can never be image. Right? So, whenever you have the cis and trans combination, that's going to be, of course, diastereomer. They are not image, right? So, let's say A and C. So, A and C are like cis and trans, right? So, A and C are going to be diastereomer pair. A is like a cis, C is like a trans, right? So in A, you have both groups in one side. In C, you're going to have one on the front and the other on the back, like a trans, right? So that's why A and C are going to be diastereomer. And then what about A and D? Same thing, right? So D is like a trans. So A and D are going to be also diastereomer. What about B and C? So B is like a cis, both on the same side, and then C is going to be like a trans, right? So B and C also going to be diastereomer. And then similarly, B and D also going to be diastereomer, right? So now what's going to be like a mirror image of each other? So cis, trans, going to be the mirror image of each other, right? So you're going to have A and B, so both have the same side, right? So this is going to be an enantiomer, and then C and D, so one front, one back, like a trans, both are trans, so this is going to be another enantiomer, right? So that's how you're going to distinguish, okay? Let me review again. So how many stereoisomers are going to be there? It depends how many chiral carbons you have in the molecule. Okay, so 2 to the power n. N is going to be 1, 2, 3, 4, 5, whatever chiral carbon you have there. So that many stereoisomers. So out of these stereoisomers, some going to be enantiomer, some going to be diastereomer. Okay. So take the same type, cis or trans, so they're going to be the mirror image. So these going to be enantiomer. If you have the cis type and the trans type combination there, so these two never can be the mirror image. So that are not mirror image you have in the combination, there's the diastereomers. So that's how you're going to distinguish. Okay? Good? Not confused? Good. All right. So now you already know that, right? So you know how many stereoisomers going to be there. So for the second example, you have 1, 2, 3 star carbons over there. You have 3 chiral carbons. So 2 to the power of 3 going to be 8 total number of the stereoisomer, right? So you have 8 over there. Okay? So now, a little bit further than the enantiomer and diastereomer. So sometimes you're going to have some specific type of molecules. It's going to have more than one chiral center. So most of the cases you're going to have 2, right? So you're going to have 2 chiral center, and out of these 2 chiral centers, you have the R and S combination. Right? So what I mean is, if you see over here, this molecule, so you have, let me write 1 and 2, okay, just to indicate that. So the chiral carbon number 1 and the chiral carbon number 2. So you have 2 chiral carbons there, okay? But if you see the R and S configuration, one gonna be the R, other gonna be the S. Okay, so we are not dealing with the condition RR or SS. You're gonna have those two, but we're gonna consider RS configuration. If you have that, then what gonna be? You're gonna have like a 2 equal half if you cut with a plane. You're gonna have the plane of symmetry within given molecule. Or you can say half part of the molecule is the image of the other half. If you cut right through it, you're gonna have 2 equal parts there. Okay? So this is called the plane of symmetry. So this is gonna contain plane of symmetry. Okay? So if you have that, this is called the meso compound. Okay? So if you pass the light through that sample, then you're gonna notice 0 rotation. So you don't observe any rotation. Doesn't mean that molecule will not rotate. It does, right? So whatever the half part of the molecule rotate in one direction, say clockwise, other half is going to be rotate the counterclockwise. So the net rotation you observe going to be 0, right? So one half going to rotate 25 degrees to the right, other half going to rotate the same magnitude to the left. So overall value going to be 0. So this is chiral molecule. So it's going to interact with the light, but you observe 0 rotation, right? So such type of molecule is called meso compound, right? Yep.
So then in a solution, would it make it optically inactive? Is that how this would work? Or?
The compound is active, right? So it doesn't mean that compound does not rotate. It does, but what you observe is like inactive. Okay? So that's the reason is one half going to rotate in one direction, the other half going to be in the opposite direction, so it's going to cancel out, so you don't observe any rotation. Right?
Thank you.
Alright, so this is meso compound. So let's see examples of that. Okay? So which of the following compounds are meso? So now for that, you're going to see the plane of symmetry if you have any for the molecule, and then you're going to see whether you're going to have the same half of one half in the molecule. If you have that, that's going to be the meso compound. Okay? So here, let's see this carbon over here. This is chiral carbon. because you have the hydrogen on the back over there. And then same for this one. So you have the hydrogen on the back over there, right? So if you cut right through at the middle by the plane, so you're gonna have the two equal half, right? So one gonna be this half over here, the other gonna be the other half over here, like that, right? So you have the plane of symmetry at the middle of the molecule. So this is going to be major compound, right? And the other one, so sometimes like you need to rotate a little bit to visualize it. So you can see something like this. So now, if you cut over here, you don't have equal half, right? So if you have double bond, there is no question of being any stereoisomer. You have the single bond there. If you recall, or if you remember butane, remember you have the free rotation along the single bond. So you have different conformations, right? So it can easily rotate. You have the single bond there. So the first thing is you try to see by rotating along the single bond, if you have any conformers that have the same half. Okay? So if I rotate about 180 degree, so I can make this OH group on the top, like on the other half. Okay? So I can have something like this. So I can have this half, I can have this half. So now you have the plane of symmetry there. So before it was not. Okay? So it also the major compound. Okay? And then the third example, so it is straightforward. You're going to cut over here, you're going to have two half, right? So again, don't view it as a 2D for OH. When you cut that, you're going to have O in one part, hydrogen in the other part. No, that's not the case. You're going to do the, like something like this one. So OH is going to be like this. So it is a little bit tricky. Always be with the 3D, right? So suppose this is oxygen and hydrogen. This is OH. You're going to cut like that. So it's going to have the higher energy, so it doesn't stay like this. So in the minimum energy, it's going to stay like that. So the hydrogen is going to be farther away from any other neighboring atoms. Okay, so you're going to cut like that. So now you're going to have the half hydrogen in both cases, half oxygen in both cases. So that's how you're going to cut the plane. Okay, so just visualize in 3D. So this is also major compound. All right. So how are you gonna determine whether it is major or not? So see the molecule. If it is straightforward, just see the plane over there. If not, see whether there is the possibility of rotation along the angle or not. If it is, you're gonna rotate about 60 degree or 180 degree. And then see whether you're going to have the equal half or not. If you have the same equal half in the molecule, then you're going to have the plane in that point, right? You're going to make the two equal half, and it is major compound. So major compound is the molecule, not the part. If you have the molecule that are the equal two parts, the molecule overall is major molecule or compound. So that's the major compound, right? So now the properties of diastereomers. So what do you think? What properties can be different based on the stereoisomeric properties? Or you can say simply based on the different position of atom in the molecule. Okay? So what can be the difference? Very simple one like a general concept is that for the intermolecular interactions, so you went through dispersion, dipole, hydrogen bond, ionic, you have different interactions in the molecule, right? So for those organic molecules, you don't have ionic interaction there. You can have the dispersal interaction over here, and then you can have the dipole. In some cases, you can have the hydrogen bonding. Most of the time, you're going to have the dipole interactions, right? So the position of one group in one position is going to affect the intermolecular interaction you have in the molecule. So that means you're going to have the different physical, mainly, and chemical in the less extent. Okay, so it doesn't mean that you don't have the difference in chemical properties, you do. But physical property is going to be more pronounced. So this is going to govern by the intermolecular force. Okay, so now you see that over here. So solubility, right? So for the same molecule, so it is the tartaric acid, that's the common name. So you're going to have the different position of the group. So you're going to have the RR in one condition, RS, which is a major in other condition. So these two molecules, same molecule, right? But you're going to have the different stereoisomers, right? So just by the difference in the position of atom, so prove that. So because of that, you can see the value 139, 125. You have the difference in solubility. Okay? And the other one, this is by the way in water, okay? So alcohol are slightly soluble in water. For the lower carbon number alcohol, if you go to the higher one, it's going to be more and more insoluble. So melting temperature. So one is going to be 171, 65. You have 6 degrees, about 6 degrees different, right? And then refractory index, you have difference on that. Density, you have difference on that. So you're going to have the difference in physical properties because of the different extent of intermolecular interactions. Okay? And then in some cases, you're going to have the chemical properties difference too, right? So in particular, that's going to be in, like I say, biophysical cases, like binding activity, how the molecule is going to bind the specific site of the molecule. So if you have the different group in different position, that can affect that. Okay, so that's why in the drug industry, whenever you want to discover one particular type of drug to bind at a certain site of the molecule, so they're going to focus on those properties. So enantiomer, diastereomer, right? So it has the application on that in drug discovery. Okay? Alright, so now the next going to be, it's not that critical over here, but if you take the biochemistry, you're gonna see this name, so you're gonna just touch a little bit. Okay? So Fischer projections. So for biomolecules, you're gonna have hydrocarbon and then different functional groups, right? So carboxylic group, alcohol, these are the primary functional groups. So how are you gonna write those stereoisomers in 2D? So that's the main idea over there. Okay, so for 3D, it's obvious we're gonna write it. But how to indicate the same 3D structure in the 2D drawing? This is called the Fischer projection. Okay, like Newman projection we did before, right? Kind of similar. Okay. So let's say you have the 3D structure like this. So you have the one group towards the viewer, other away from the viewer, and then you're going to have other two in a plane of the paper. This is the normal drawing in 3D, right? So now, you're going to do the same thing for the visual projection. How are you going to draw it? So this is how I'm going to draw, right? So this is the visual projection. So you have the 2D. You don't have dotted line there. You don't have bold line there. All normal line, right? That means all are on the plane. But they have a specific meaning when you draw that. Okay? So here, you're gonna slightly rotate the 3D structure. So we're gonna start from 3D because this is obvious. We know that is structure, right? So you're gonna slightly rotate that so that two gonna be on the back and then two gonna be on the front, right? Like something like this one. So two gonna be on the back and then two gonna be on the front, right? So normally in 3D, how we're gonna draw is like this. Let me show you, make it easier. So in 3D, you're gonna keep these two in one plane, and then one gonna be on the back, other gonna be on the front. So this is how you're gonna draw. Okay. So if you rotate slightly, then what's gonna happen is you're gonna have two on the back, two on the front. Right? So just rotate slightly. Then you're gonna have the structure like this. So this is gonna be like that. Okay, so you're gonna have two bold lines towards the viewer, and then you're gonna have two dotted lines away from the viewer. Okay, so two like that, two away. Right? So then what you're going to do is, so you're going to have the horizontal line for the two groups that are towards the viewer. So you're going to write always the horizontal line for that. Okay? And then two groups that are away from the viewer, the dotted lines, you're going to write the vertical line for that. So this is the vertical line for this one. That's how you're going to draw. So in any visual projection, okay? So take the carbon center and then see the vertical line and the horizontal line. Okay? So the vertical going to represent two groups are away from the viewer in 3D. Okay? And the horizontal line you have going to be towards the viewer. Okay? So that's how you're gonna draw it. So you have more examples over here, right? So you can go through that. And this is also another example. That's it. Good? How do you feel this chapter? Easy or confusing?
I need practice.
It's not too bad.
Yeah, I'm gonna spend a little bit more on the review. Okay?
No, I got it. I'll probably do today. Try the homework.